So, we're going to start today by actually talking about reviewing our double and single replacement reactions that we talked about last week. So, I created this chart for you guys. Obviously, you can't really copy paste it necessarily because it's on the slide. But what I'd like for you to do is either in a Google Doc or on a piece of paper, go ahead and set up your own chart where you list out all 5 types of reactions, give a box for a description, and then give examples. And this is going to help you stay organized and be able to reference back to your notes quickly to see which type of reaction is happening. So we've already talked about single and double replacement reactions. So what I want you to do is set the chart up and then actually fill in the description and the examples for single and double replacement reactions. And I'm going to give you guys probably, about 5 minutes to do this, and then we will go over it and start talking about synthesis and decomposition reactions, which are a little more complex than single and double reactions. All right, so I've already started filling stuff in here. You guys do not have to write the same thing as me. In fact, I'm going to ask you to share what you wrote. But hopefully you've gotten your chart set up either in a Google Doc or on a piece of paper, and you are working on your description / your examples. Hi, Logan. Welcome to the virtual session. All right, so about 30 more seconds here, and then we're going to start going over the first 2 descriptions here. Okay, so we're going to start going over this, right? Essentially, I want you guys to have a chart where you can see the types of reactions, what that would look like in a description, right? And then an example. Because when you are faced with trying to predict the products of a reaction, and you have to choose from all 5 of these options, it can start getting really, really, really confusing. So these are 2 review ones that we did last week, single replacement and double replacement. So single replacement, right? What did you guys write? I mean, you can see what I wrote, but do you have anything to add to what I wrote here, or would you like to share what you are writing in your chart? If you do, go ahead and paste that into the chat, but I'll share what I wrote here. I wrote one element replaces another, usually a metal. Requires the activity series in order to determine if the reaction happens, right? And some of the reactions we saw last week, we saw this exact thing where they did not happen because the metal was not reactive enough to replace another. So these are the kinds of things you want to note down, right? Do you need to use extra charts or extra notes in order to figure these things out? For the example, I did one with lithium and zinc. 2 lithiums plus zinc chloride will actually cause lithium to replace zinc, right? And we'll get lithium chloride and zinc. I guess it should be plus, oh no, just 1 zinc. So also recall our steps from last week, which will be steps that you'll use for a large portion of the class. I'm going to write these over here. They're not actually synthesis, but steps include predict products, right, which would be using this chart. Balance, or actually, let's see, subscripts, which come from bonding, then balance your equation. And one of the things that I am seeing a lot is people are not balancing the final equation once you have everything in place, right? So what that means is literally looking on both sides and seeing, are there the same amount of things? There's 2 lithiums on the left, are there 2 lithiums on the right? If there were 50 lithiums on the left, you would have to have 50 of them on the right. So just getting your bonding correct is part of it, and a lot of times that will help with the balancing of equations, but you do need to check after, right? And you'll notice here, especially in the double replacement reaction, which we'll look at in a second, there is some balancing happening quite a bit actually. So double replacement reaction, we talked about last week, 2 ions switch places. Right, that's it. Usually they are polyatomic ions, or one of them is a polyatomic ion. So again, having your polyatomic ion chart or having access to that would be incredibly useful for this. An example here, we have aluminum nitrate, right, plus sodium hydroxide, and we're getting aluminum hydroxide and sodium nitrate. So here's a great example where, figuring out the charges at least, we can see that aluminum has a charge of -3. Oh, Catherine, you're having a lot of tech problems, huh? It's okay. This is being recorded, so you can always go back and watch it again, especially if you're getting, just parts of it. Okay? So just hear as much as you can right now. So remember, we find those charges from the periodic table. Aluminum is in group 3. If you recall from last week, we talked about how to do this. But aluminum would have a charge of +3, and nitrate has a charge of -1. So we need 3 of them to bond with 1 aluminum, right? Because we need our charges to equal. Sodium and hydroxide are a little different, right? Hydroxide also has a charge of -1, and sodium has a charge of +1. So those 2 actually just bond. We don't need to add any subscripts. On our product side, we see 3 hydroxides with aluminum, following the same logic here, and we see just 1 nitrate with 1 sodium. Once you've done that, that's where you come into the balancing. That's where these 3s come in, right? Because if I look at my whole equation, I notice that on this front end here, I actually have 3 nitrates. Well, I have to have 3 nitrates on my product side then as well. So if I place a 3 in front, it then changes my sodium. So I have to come over here to my sodium hydroxide and add a 3, right? And then conveniently, you're done. But balancing can be hard. If you're struggling with that, it might help you to make a T-chart and write out how many of each one is on each side and play around with trying to make them equal. Some things are so easy to balance, it'll take you 4 seconds. Oops. Then some things it'll take forever, right? Because you keep changing it and then the other one changes. And so if it does take you a while, that's okay. That's not completely unheard of. Okay, so I just erased my example, but you guys get the idea. So we're gonna come back to this in a second, and we're gonna actually add descriptions and examples for synthesis and decomposition. We're not going to talk about combustion reactions today, but those are another lesson that you will do. So you can add your own description and an example for those. Combustion is actually not super hard to recognize. So that one, you probably don't need any extra help with that one. So let's review our stuff we learned last week, single replacement reactions. So these 2 reactions, I'm going to give you guys about a minute and a half-ish. Figure out if these reactions would happen. Okay, so let's start going through this. What did you guys get for the first one? Will sodium chloride and iodine, will there be a reaction? And if there is, what will the products be? What did you guys find out from using the activity series? Thank you, Logan. You're 100% correct. There would be no reaction. So how do we figure this out? Last week, we talked mostly about metals, right? So I actually picked these 2 examples to show you that the same thing can happen with halogens, which if you saw on the activity series, right, over here on the far right, you have your halogens, chlorine, fluorine, bromine, iodine. And chlorine is the most reactive, iodine is the least reactive. So in this case, we want to know, will iodine replace chlorine? It won't, right? Iodine is not reactive compared to chlorine. So all you would do for this reaction is write no reaction. Nothing would happen, literally. What about for the second one? What did you guys get? If we have lithium bromide and fluorine, will we get a reaction? And if we do, what would our products be? I'm going to untangle my cords while I wait for you guys here because my computer is definitely going to need a charge in a second. But what's going to happen? Look at the activity series, right? Figure out, will fluorine replace bromine? What would the products be? All right, guys, I'm a little worried because nobody's talking to me here. No one's saying, I don't know, I'm not sure, right? This is what we covered last week. So this is not new. This should be a review. Logan's the only person talking to me right now. Thank you, Logan. But otherwise, right, if you guys aren't talking to me, I'm not going to give you credit for being here, right? Because how do I know that you're even paying attention if you're not responding at all here to something that's review? So Logan's saying fluorine will replace bromine. Well, I agree, right? Looking at the activity series, fluorine is above bromine, meaning fluorine's more reactive, so fluorine will replace. So would our final products be what Logan has here? Yes, right? Lithium fluoride. Do we need 2 fluorides with that lithium? Would be my question. Let's think about our charges here. Lithium has a charge of +1, right? We get that from the periodic table. It is a group 1 metal. Fluorine has a charge of -1. We get that because it's a halogen, right? And it will always gain an electron, giving it a full shell and making it have a -1 charge. So we actually don't need that 2 there, Logan. Although that's a good guess because you saw a 2 here, right? Fluorine will never exist by itself. Fluorine will be a diatomic molecule, meaning that it will pair up in nature, right? So this is actually just representing fluorine by itself. It would never just be 1F. It's always going to be found as a diatomic molecule. So we don't actually need the 2 after the fluorine, but, right, we will need a 2. We also are going to then get our bromine by itself, which you guys may not know this, but bromine will be the same thing. It will be a diatomic molecule. It will bond with itself, right? Just like oxygen does. When we see oxygen, we see O2, right? When we see hydrogen, we see H2. These things don't just float by themselves, right? They have to be paired. Now, to balance our equation, right, this is where it will get a little bit more complicated because we do have 2 fluorines over here. We only have 1 on our product side. So, whoops, I did not mean to completely erase what I just did, but I will write it out again. Okay, so in order to balance our equation now, we do add a 2 in front of our lithium fluoride so that we have 2 fluorines. Now we have 2 lithiums. Well, we need 2 lithiums on this side. If we add a 2 in front, we will also then balance our bromines because bromines will be a diatomic molecule as well. So this reaction does happen, right? Why? Because fluorine is more reactive than bromine. Once you've figured out if the reaction happens, replace your halogen, your metal, whatever it is, figure out your bonding, right? Look at the charges, look at the periodic table, use that to help you. And then final thing, balance your equation. Okay, so this was review. If this seems very, very confusing to you, go back to last virtual session, the one from last week, and watch the virtual session on this where I go in more detail, right? But we need to move on to the new topic now because I don't have time to go over this again. So, synthesis reactions. Well, what does the word synthesis mean? It means to make or build. So in this case, a synthesis reaction will always look like this. A plus B will yield AB. Now, will it be one element by itself? We're about to see. Seems very simple, right? This is actually really, really easy to see and go, that's a synthesis reaction. Now, the hard thing is predicting them because there's a million types, Not a million, there's 4. So we have 4 types of synthesis reactions. This is 100%, all 4 of these should go in your examples box from the chart that we made in the beginning of class, because to predict products, you're gonna need to see these. First type we can have is a metal plus a non-metal. Sodium is a metal. Oxygen is a non-metal. In this case, when we combine them together, right, they do form sodium oxide. 2 nonmetals, in this case, sulfur and oxygen, right? Again, if you're not sure, find the element on the periodic table and see where it is. Is it a metal? Is it a non-metal? Is it a metalloid, etc.? So 2 nonmetals is a pretty easy one to recognize because there's not that many nonmetals. Metal oxide plus water. Okay, water, easy to recognize. Metal oxide, it just means a metal and an oxygen that happen to already be bonded together. So in this case, we have calcium oxide plus water. We'll produce calcium hydroxide. The same thing can happen with a non-metal oxide, right? So you can end up getting a sulfur oxide here, 2 nonmetals, right? Or a non-metal oxide, technically, plus water. And again, this will actually produce an acid. So synthesis is easier, I think, than decomposition, which we'll look at in a second, because decomposition is when it's going to break apart, right? So then you kind of have to know what is made. But in this case, if you see 2 things becoming one thing, you should immediately think synthesis. And if you're not sure, right, for example, the products maybe aren't shown. Maybe it's a question on a quiz where they're asking you to predict. Is it a metal and a non-metal? Is it 2 nonmetals? Or is it a metal oxide or a non-metal oxide and water? If it's these combinations of things, it's most likely going to be a synthesis reaction. And notice, you can't do single replacement or double replacement necessarily, right? The ones with water might be tricky because you might think, oh, maybe you could do a single replacement reaction here, right? But you can't. Usually when something's reacting with water, it's not going to be a single or double replacement. So that is something that you can just use as a general rule. Otherwise, right, what's going to happen here? What would replace between sulfur and oxygen? Don't know, right? There's nothing to replace. They have to combine to make something new. Otherwise, what are they going to do? All of these types of reactions for synthesis reactions, there's no chance here that they won't happen. Now, there are reactions that don't happen. But in this case, there's no activity series or anything that you have to use to tell you if the reaction will happen. You can assume that they will happen if they are given to you. So again, these 4 examples you're going to want to put in your example box. And in terms of describing synthesis reaction, right, you could write this definition here to make or build. Or I like how Logan described it here, the production of chemical compounds by reaction from simpler materials. Yeah, right, and it makes sense. We're taking 2 simpler things, combining them together to make something more complicated. Again, if you see the full reaction, it's really obvious. When we take away those products and you have to predict, that's when it gets hard. So use these examples, right? Even if you just write the white parts here, metal plus non-metal, 2 nonmetals, metal oxide plus water, non-metal oxide plus water, that will help give you some hints about what would happen, right? They're going to form together into one compound. All right, any questions about synthesis reactions? Okay, we're going to look at some examples in a little bit. But before, decomposition, right, is the opposite. Decompose, right, means to break down. Most of us are familiar with that term. In this case, we're going to be taking AB, and it's going to break apart into A plus B. So we're doing the opposite of a synthesis reaction. These are a little bit more complicated, right? At least in my opinion. Again, really easy to recognize when you see them. If the whole equation's there, you go, oh, that's decomposing. It was one thing, now it's 2. Predicting, it gets harder. So you'll notice these are pretty much direct opposites of the synthesis reactions. Makes sense, right? But they're called different things. In this case, we can have a decomposition reaction that breaks down into binary compounds. What do you think binary might mean? Looking at what happens in this one. What is a binary compound?
Yeah, right. I think it depends on the twist.
What do you guys think? What does binary mean? Thank you, Logan. Binary means two. Good. Yeah. So perfect application, right, of the actual word. It means you're going to get two compounds, right, or two elements in this case. So sodium and chloride will decompose to be sodium plus chlorine, right, or chloride. So yeah, literally it just means you have two elements bonded and they break apart to be by themselves. Metal carbonate and metal chlorate are kind of similar, right? Metal carbonate, you will end up getting carbon dioxide as well as a metal oxide. Metal chlorate, right? Notice that means that they have a chlorate polyatomic ion attached to the metal. You'll get calcium chloride and you'll get oxygen, right? So chlorates will release oxygen and carbonates will release carbon dioxide. Again, these are things that you can use your notes for. So have these examples, right? Again, all of these things are based on patterns. So once you start seeing the patterns, it becomes easier to recognize. A metal hydroxide, right, meaning it's a metal with a hydroxide group, will produce water plus a metal oxide of some kind, right? So really the thing here is this is telling you these words are describing your reactant. Your binary compound just has two elements. Your metal carbonate has a metal and a carbonate. Your metal chlorate has a metal and a chlorate. Your metal hydroxide has a metal and a hydroxide. Imagine. So those words are describing, just like Oliver said here, binary means two, and in this case, we're breaking apart into two elements. So metal carbonates will always produce carbon dioxide. Metal chlorates will always produce oxygen. Metal hydroxides will always produce water. Figuring out what the other compound is can sometimes be really obvious and sometimes not. Then we have an oxyacid, which is an oxygen-containing acid. For example, sulfuric acid, H2SO4. Again, this will also break down into water plus something else. So the hydroxide and the oxyacids, right, because hydroxides are bases. So bases and acids will always break down into having water as one component in them, which is a good, helpful thing to know. However, right, again, there's a lot of different types. So how do we actually solve this or utilize this is what you might be thinking. Well, let's predict. Let's try to predict what some of these products would be. We're going to do the first two together, and then you will try the second two by yourself. So first reaction, nitrogen and hydrogen. What are we thinking? Is this going to be synthesis or decomposition? Synthesis, right? Oliver's 100% correct. We have two things, we must be combining them together, right? Because what are we going to break apart? They're already broken. Okay, so then what I would do is I would go back to my synthesis notes, figuring out which ones of these things I have. Do I have a metal and a non-metal? Well, not really, right? It looks like I have two nonmetals. So two nonmetals, all I do is combine them together. Well, that seems pretty obvious and easy. So let's see if we can do that. So what do you guys think? What would N2 and 3 H2s become as a compound? What elements do we have? Well, we have nitrogen and we have hydrogen, and we need them to combine together. So personally, what I would do is I would find out my charges, right? And I wouldn't even, I wouldn't even write a compound yet. I would just figure out, well, what are my charges? Nitrogen has a charge of what? If you're not sure, right, how could you figure it out? Well, you go to the periodic table. So, my favorite one, dynamic periodic table. Nitrogen, where is it? It's over here in group 5, meaning nitrogen has a charge of what? Well, it has 5 valence electrons, which means nitrogen will gain 3 electrons to have a full shell. So nitrogen's charge is -3. Good job, Logan. So in this case, our nitrogen has a charge of -3, and hydrogen has a charge of what? +1, right? It's group 1, top left corner. So how many hydrogens do we need to go with 1 nitrogen? 3. So all we're going to make here as our final compound is NH with a subscript of 3, right? Which if you wrote that out by hand, or if you took the time to do subscripts, which I don't because I'm pretty lazy, we would have our 3 down here as our subscript. Okay, so are we done? We created our synthesis compound here, but are we done? Is our equation balanced? It is not. So how can we balance our equation? I like to start with hydrogens personally. I look over here, or you could do nitrogens even, doesn't really matter. But over here I see I have 6 hydrogens. And I only have 3 here. So my first instinct is to add a 2 in front of my NH2, which conveniently works because then I have 2 nitrogens, 6 hydrogens, 6 hydrogens. So this would be the final answer here for this equation. N2 plus 3H2 will yield 2 NH3. Okay, let's try the next one. So, just from looking at it, what do you think? Synthesis or decomposition? Thank you, Vitali. Decomposition, right? We only have one thing. How is it going to synthesize? It can't. Could it be single or double replacement? Again, no. What would be replacing? Nothing. So now we have to determine, well, what type of decomposition is it? So go back to your notes. Let's look at what we have. We have a metal, right, silver, and an oxygen, an oxide. So we have a metal oxide. So do we see metal oxide on here necessarily? No. What I do see, though, is binary compound, where I just have 2 elements. So that, to me, sounds like, okay, that could be what I have, right? I don't have a carbonate. I don't have a chlorate. I don't have a hydroxide. I don't have an acid. So none of those could be right. Okay, so let's look at it. Silver and oxygen, maybe they'll just break apart by themselves. That's what I would predict here. So silver plus oxygen. And we know about oxygen that it will bond with itself, right, to be a a binary compound, there's only a few elements that have to do that. Oxygen, the halogens, hydrogen. I feel like there's 8 of them that have to do that. Metals don't usually do that. So silver will be immune to that, essentially. But what I do see here, though, is my equation balanced? Do I have the same number of silvers to start? No, right? I have 2 silvers here. I have 1 here. I have 4 silvers here, excuse me. And I have 1 here. I have 2 oxygens here, and I have 2 oxygens here. Okay, so oxygens are fine. Silver, I would need to put a 4 in front of, so that my equation would be balanced. Okay. You guys try number 3. We'll start together, though. What do you think it is? Synthesis or decomposition? Synthesis, right? We've got 2 things. Can't be single or double replacement. So they must be getting put together. So again, maybe write out what it is. H2 plus Cl2. Diatomic elements there. And go back to your synthesis notes, which, by the way, this PowerPoint will be posted for you so that you can access it. And looking at what you have, see if you can figure out what the products would be.
Sometimes I know what I'm trying to say, but the words don't always match exactly. No, especially when I can't do it.
If anyone wants to take a guess, right, in case you didn't write down what the original question was, right, it was H2 plus Cl2 yields what? So what do you guys think? What would we get here? If you're not sure, right, look at the models. Is this a metal and a non-metal? No. Is it 2 nonmetals? Yes, right, hydrogen and chlorine, both nonmetals. Looks to me like we're just gonna stick them together. Right, so that's pretty easy. Logan's saying H2Cl2, that's a good guess. But let's think about our bonding. What is our charge on a hydrogen? +1. Hydrogen would be +1. And chlorine would be what? Chlorine would be -1. So do they need any subscripts to bond? No, right? They just straight up become HCl. So you're going to be tempted to do exactly what a lot of you just did, which is take these 2 and literally just put them together. Sometimes that will work, but not always. Always check your bonding. Is that how a hydrogen and a chlorine would bond? Right? If it is, then great. If it's not, then adjust. So they don't need any subscripts. Exactly. If the numbers are the same, then you just remove them. Exactly. Although not always. In this case, yes. Really you want to know about the charges. But you're right, Logan. If for some reason you were working on your charges and you had like H3Cl3, right? Like you had this. Well, you're basically saying that they bond on a 1-to-1 ratio. So you don't need those 3s, right? Because they're the same. So you're exactly right. That could be a way to think about it, right? Because then it's almost like math where they're obviously in equal amounts. Now, is our equation balanced though? Because we do have 2 hydrogens over here and 2 chlorines over here. Well, I see 1 and 1 on this side. So now we do our actual coefficient, right? We put our 2 in front of our HCl. so that we do have 2 hydrogens and 2 chlorines. But what we're really saying is that hydrogen and chlorine combining will create 2 moles of hydrochloric acid, right? Because this is actually creating an acid. So this is telling us the amount that's produced, which will become important later. Okay, so let's try the final one. Okay, go to erase all my stuff here. So final example, 2 lithium hydroxide. So what do you think, just from looking at it, is it going to be synthesis or decomposition? Decomposition, right? Probably, like I said, these are really easy to see. Then the predicting the products part is where it becomes a little bit more complicated. Okay, so we have 2 lithium hydroxide. So we know it's a decomposition reaction. Which one is it going to be? Well, go down your checklist. Is this a binary compound? No, because I see an OH. I see 3 things, not 2. So nope. Is it a metal carbonate? I don't see a carbonate. Is it a metal chlorate? Again, don't see a chlorate. Is it a metal hydroxide? Yes, it is. Okay, so what does that mean? That means we're going to end up getting water plus a metal oxide. Okay, so we know we're going to get water, and there's no reason that you can't write the H2O first. And we're going to get a metal oxide. So we have lithium, and we're going to have oxygen. Now, will lithium and oxygen bond on a 1-to-1 ratio? Let's think about their charges. Lithium has a charge of what? It's a group 1 metal, just like hydrogen. Lithium has a charge of +1. What about oxygen? -3 is a good guess. You're close. -2. Good, Oliver. Right? Remember, oxygen has a valence of 6, which means it needs 2 electrons to fill its shell. So it will take on 2 electrons, which will cause it to have a charge of -2. Right? It has 2 extra negatives. So will lithium and oxygen bond in a 1-to-1 ratio? No, right? Logan is suggesting exactly correctly here. We will need to put a 2 underneath our lithium, which I kind of didn't leave enough space to write it there, right? But you're right, it will be lithium with a subscript of 2 oxide. Okay, so again, we have a metal hydroxide that's getting broken down into a metal oxide plus water. Oh yeah, it's okay. I can't even tell the difference, really. Okay, so now we do our check, is it balanced? Well, I see 2 lithiums here. I see 2 lithiums here. I see 2 oxygens here. I see 1, 2 oxygens here. And I see 2 hydrogens here. And I see 2 hydrogens here in water. So this one actually is perfectly balanced. I don't need to put any additional subscripts. Coefficients. I just want to call everything a subscript. So I don't need to do anything else. That one's done. Okay, how are you feeling on a scale of 1 to 10 about predicting these products yourself? Using these notes, right, using the stuff that you've learned, right? 10, I could do it all day. 1, I am so confused, I have no idea what it is. All right, I'm seeing 6.7, 7. Okay, so guys, just go through the steps, right? First things first, which type of reaction is it? If it's single replacement, make sure you have your activity series, find out if it's even going to happen. If it's double replacement, Should be pretty obvious because two things are going to change places. That's all ions. Synthesis, easy to see. Two things coming together as one. Decomposition, one thing coming apart. Then you have to do your bonding, right? Honestly, what I would do is have a periodic table where you write the charges. Nothing there, that isn't even considered cheating. You are welcome to do that, right? The charge for hydrogen is 1. All group 1 has a charge of +1. All of group 2, oops, what did I just do? All of group 2 has a charge of +2. Metals are different, but they will tell you usually by what they're bonded with or by their name. All group 3 have a charge of +3. Group 4 will never be in an ion form, so you never have to worry about it. Well, except 10. 10 might. But again, it will tell you based on what it's bonded with. Nitrogen's group has a charge of -3 because now we're getting to the side of the periodic table where electrons are accepted. Oxygen's group has a charge of -2. And then finally, our halogens have a charge of -1. Again, noble gases, full octet, they're not going to be involved in these reactions. So have your charges written, right? There's no reason that you can't use that to help you. That seems to be what is stopping a lot of you guys, is you're like, oh no, what's the charge? Well, put it on the periodic table and look at it, right? Find your element. Oh, here's lithium. It has a charge of +1, right? That's gonna make your life so much easier. And then you'll actually probably eventually have most of them memorized, like I do, which is creepy, but it happens. So get your charges written out, practice doing that, right? When things bond, make their charges cancel. They should be neutral. They should be a nice neutral atom. Or I guess really a compound, but a neutral compound. Okay, so now I'm gonna ask you guys a couple questions. So next week, right, we go on break on that Thursday. Do you guys want to have a virtual session? I was not planning on having one. However, if you'd like to, we could go over any of these things. We could go over bonding. We could go over balancing of equations. We could go over these reaction types again. Or we could not have a session. So I want you guys to tell me what you think is going to be most useful for you. If you'd like to have a session, yeah, maybe an overall review. So maybe different reaction types for every single one. Or are you feeling like you have enough information to do this by yourself? So Logan says a short review. Let's see what other people think. Okay, so Oliver, you won't be able to attend, right? And I figured that a lot of people would probably be unable to attend next week as well. Maybe it's optional review, okay? Yeah, so people don't have to attend, but you can if you want help. Okay, so that's a choice. Will you attend, Logan? I hope so. Okay, so Oliver won't be attending. Logan could potentially do a review. What are other people's thoughts here? Aiden says review. Okay. What about Vitali and Catherine? I don't know, Catherine, if you're having tech issues right now. You don't know if you'll be able to attend. Okay. Okay. So then we will do a little review next week. Yeah, your finals week, yeah. I know, there's a lot going on. So I'll create a slide with some reactions on it, and we'll do this exact thing that we did today. Practice predicting the products, identifying the reaction, doing the charges, doing the balancing, right? So I'll just come up with five examples of different types of reactions, and then you guys come if you can, and we'll do a little review. I won't penalize you though if you're not there. Otherwise, right, if you're going through these lessons, let me know if something in particular is really hard, right? Send me an email. You could even just send me an email and say, hey, can you go over finding the charges in the virtual session? Can you go over this? next, or when we come back from the break, we will be doing limiting reactant and stoichiometry, which is probably the hardest stuff that we've done. So this is the time to ask your questions because this stuff is just going to continue to be used into the next topic. All right, otherwise, you have the decomposition and synthesis quiz due today, right? So for being here, I'm typing a code word into the chat right now that you can use to get 5 points added to your quiz. So just put that in one of your answers. You can put it in the comments. You can email it to me separately, right? Whatever's the easiest way for you. But that will get you 5 bonus points on the decomposition and synthesis quiz that is due today. Now, you don't have to take it today necessarily if you're not quite there and you need to take it tomorrow, right? That's fine. Just write the word down in your notes so that you have it. All right, otherwise, I will see you guys next Tuesday for a small review if you'd like. And then otherwise, we'll resume our sessions once we come back from break. Okay? I'll see you guys soon.